superimposed dead load. So final load combination will be this 1.2 plus 0.14 dead load, and these terms are same. And the final will be 1.34 dead load plus 1.0 EQH plus 30% of EQY, because in earthquake we have to consider the orthogonal effects. But those orthogonal effects you do not need to consider in the wind loading. For wind loading, you have to apply only one direction. Here in earthquake can come in both directions, so we have to consider 30% of another direction. Same thing for the 0.9 dead load combination. So in 1.2 dead load combination, we want to have larger compressive demand. So we add that 14% of dead load in the load combination of 1.2 dead load. But for 0.9 dead load, we want to control the we want to consider the tension effect or uplift effect. So we subtract 14% dead load in that load combination, so it will be 0.76 dead load. You can consider that 0.14 positive here, but it will not govern the design. So we reduce the number of load combinations in the design. Another thing is this 0.5 dead load. If you have the live load of 4.8 kilopascal or more than that, or storage live load, so in that case you have to use 1.0. But here we are using 1.92 kilopascal only, so you can use 0.5 dead load. So these are the load combinations you have to add in your design load combinations in the model. And this EQH, EQY will be the response spectrum cases, not the equivalent static cases. I will continue the shear wall and coupling beam design. In tall buildings, we use the shear walls to resist the shear moment and axial forces to prevent the side sway of the building, especially under the strong earthquakes and winds. And also those shear walls has to resist the main forces from the lateral loads without significant strength loss, strength as well as the stiffness loss. When we determine the when we determine the shear wall thickness, there is no minimum thickness limitation in the code ACI 318. But we should use at least 200 millimeter thickness of the shear walls as a critical lower limit if we design the walls as a special reinforced concrete shear walls. If you make thinner than that, there might be constructability issues during the construction. Also, it might have the local buckling problems. In shear walls, normally in the high seismic zone, we provide the special boundary zones at the corner of the wall. In that case, there will be large vertical reinforcement as well as the large confinement in those zones. So, if we have those special boundary elements, we should use at least 300 millimeter thickness in the shear walls. Because if you use lesser than that, there will be congestion of vertical reinforcement and the confinement reinforcement. And if we have the coupling beams connecting to the walls, we should use minimum of 350 millimeter. Coupling beams, the type is conventional reinforced coupling beam, which has the longitudinal reinforcement and the stirrups and confinement. If you have another type of coupling beam, the diagonal reinforced beams, which is coupling the walls, you have to increase the minimum thickness to 400 millimeter. Diagonal reinforced beam means the main reinforcement is placed in diagonal position. Bundle of reinforcement is placed, and if it goes to the boundary zone of the shear walls, there will be construction problems if you use smaller thickness. Okay, reinforcement ratio. In the shear walls, the minimum reinforcement ratio for longitudinal reinforcement, that one is the vertical reinforcement, and transverse reinforcement is 0.0025. Not like the columns. In columns, the minimum reinforcement ratio is 1%. Here it is 0.25%. But if your shear stress is small, those reinforcement can be reduced further. The shear stress VU is less than 0.5 phi into VC. If your shear wall is short or squat walls, H over LW, H is the height of the wall divided by length of the wall, is less than 2. Rho T transverse reinforcement should not be less than the vertical reinforcement, because in those walls both vertical and horizontal reinforcements are resisting the shear. Here, this is the typical layout of the shear wall. At the ends, we use the boundary elements with large vertical reinforcement and also confinement. And in the middle, we normally use the minimum reinforcement, vertical reinforcement, and also we have to provide the horizontal reinforcement to resist the shear. So, the vertical reinforcement in the shear wall is designed for axial and bending moment coming from the lateral loads and vertical loads. And horizontal, this horizontal reinforcement is designed for the in-plane shear to coming to the wall, and these confinements are provided to improve the ductility of the shear wall, because under lateral load the shear wall will have in-plane bending moment, and in this at the corners you will see the large axial stresses, compression and tension. But for earthquake loading, this one will be cyclic, so this side will have both tension and compression. This confinement is especially for the compressive stresses. If large compressive stress occur, the concrete is brittle, so if we provide the good confinement, it will become more tactile. This is minimum reinforcement requirement from the code ACI 31814. Here you can see that in cast-in-place concrete, if shear stress is less than 0.5 VVC, the minimum transverse reinforcement can reduce until 0.2%. We normally consider the walls are slender if H over L is greater than 2. Height of the wall divided by length of the wall is greater than or equal to 2. In those walls, the response is mostly like flexure cantilevers. And also we prefer the inelastic behavior yielding in flexure at the base of the wall without the shear failure. So we provide the good confinement for the ductility and the flexure response, but we have to provide the enough shear capacity of the shear wall to prevent the brittle failure. Another type is squat wall. That wall H over LW is less than 0.5. They resist the forces in diagonal stress mechanism, and both horizontal and vertical reinforcement resist the shear demand. That walls transition between those two extremes response in both failure modes. I will focus on the slender walls. In slender walls that we use in the tall buildings, when we design the walls, for example, this is planar wall, we design the wall to have flexure yielding under earthquake, mainly at the base of the wall. This is the critical section for the flexure. This is like acting as a cantilever. If we have the wall which has the coupling beams connecting to walls, in that case we allow shielding in the coupling beams as well as at the base of the wall. But we prevent all shear failure modes of the shear wall, foundation and structural diaphragms. So shear failure modes we prevent, but we allow flexure yielding under in the walls. So when you design the shear wall, you have to select the critical section of the wall to allow yielding and provide the good confinement, the boundary zone reinforcement in those locations. So from your analysis, from ETAB's model with design load combinations, let's say this is the bending moment diagram of the wall from the load combination. So in those at the base of the wall, we will provide the vertical reinforcement just enough just enough to satisfy that moment demand, and then upper level we provide more reinforcement. So if strong earthquake coming, this wall will be yielded in that location, but we have to provide the good ductility. But upper levels, we can reduce the ductility requirements. We can relax the confinement reinforcement. But in tall buildings, the higher modes are also significant. You can see in the model participating mass ratio from your project, all 90%, more than 90% of the modal participating mass is not participating in first mode. Only 50-60% of mass is participating in the first mode. The higher modes are participating in 20% or 30% ratio. So those higher modes can cause the yielding of the wall, maybe upper levels, around mid-height of the building. So in that case, we have to provide good confinement at the mid-height of the wall as well. So to improve the ductility of the wall and the flexure mode, we have to design the wall with low compressive stresses and shear stresses. Although you provide the good confinement, if your shear demand or compressive demand in the wall is large, the ductility will be reduced. And also you have to provide the confinement, and also we have to avoid the splice failure. That means you provide the good vertical reinforcement to satisfy the moment demand and shear reinforcement to resist the shear demand. You have the good the capacity, strength capacity of the wall. But if you do not provide proper splices of the vertical reinforcement during the construction, those splices can be failed during the cyclic loading. So you have to provide proper splices. And axial force should be well below the balance point. In UBC 97, it suggests that axial compressive force should be 0.35 P naught. P naught is the axial compressive capacity of the wall. So 35% of the capacity of the wall, the demand should be less than that. But in ACI 318, there is no limit like this one. But ACI 318 suggests the compressive strain in the concrete that 0.003 should not reach before the tension reinforcement yield. It means that under this bending moment, this side has tension. Okay, this side has compression. The compressive strain in this side should not reach 0.003 before this side reach the tensile strain in steel 0.002. It means that if it reach 0.002 first, this one will yield. The steel is yielding first. Concrete is not failed in compression. But if this one reach 0.003, it means that this one will fail in compression first before this steel yield. It looks like over-reinforced beam. In over-reinforced beam, the failure comes first with the compression failure. So in shear walls also, the code suggests to design to avoid the compression failures. Another one is to reduce the shear stresses. Good design practice, the shear stresses in the shear wall should be 0.33 square root of f prime c to 0.5 square root of f prime c. But these values are not mentioned in the code. This is coming from other textbooks. But if the flexural ductility demands are low, let's say in the upper level, you can allow large shear stresses. So these are the failure modes due to the concrete crashing and reinforcement buckling. For example, this is the shear wall, and this is the boundary zone at the corner of the wall. And if we do not provide proper confinement, this wall will fail in concrete crashing. The concrete becomes brittle because you do not have good confinement, and it reached 0.003 strain value in compression, and it will crash. And not only that, the reinforcement will be buckled. Another one is the left splice failure. We confine the concrete based on the bending moment diagram, and we, for example, at the base we design the shear wall bending moment capacity just to satisfy the demand forces, and we provide the reinforcement. But if we need to, but in construction we need to splice the reinforcement, because you cannot get very long reinforcement throughout the height. So when we splice the reinforcement ratio will be increased, because one bar will be doubled. If you have, for example, if you splice 20% of the vertical bars, there will be 20% in steel increase in steel area. In that case, bending moment will be increased. If bending moment increase in that, for example, you have spliced between ground level to level 1. So between that ground level to level 1, the bending moment is increased. So previously we assumed that ground level to level 1 shear wall will yield and we provide confinement. But that, because of moment capacity increase, that location, the yielding location is shifted to the other floors, upper floors, which may not have good confinement. So these things we have to take care in the design. And also during the large during the multiple yielding cycle, that lap reinforcement can be unzipped during the ground shaking. In that case, you will see the vertical cracks in the shear walls due to the left splice failure. You have enough moment capacity, but due to the failure of the left splices, you cannot achieve the design moment capacity. In ACI 318, it suggests that the lap splice should have 1.25 times length required by FY in tension, but it doesn't suggest any confinement in the lap splice zone. But good practice, we have to provide the good confinement when you have the lap splices, although the code doesn't recommend it. Another type of failure is the local buckling. These things happen in the slender walls. So, although you have enough capacity, but if large compression happen, the wall will be buckled before yielding in flexure. This one can also happen. This one is happening due to the large compressive stresses, but the tension strain occurred in the first cycle of this end. The reinforcement, vertical reinforcement are yielding, and another cycle it is compression, and this asymmetry of the reinforcement yielding can create the buckling of that wall. For example, one side reinforcement is yielding, this side is not yielding. So in that case, this can create the local buckling. So if the two curtains of wall, one side is yielding and one side is not yielding, that one can create the out of plane curvature and buckle the wall. So to prevent the local buckling, we have to provide enough thickness. HU is the height of the wall, not total height from ground to the roof. That one is the height of the wall between two lateral supports. For example, 1 story height of the wall. And B is the thickness of the wall. That HU over B should be less than 10 within the intended hinge region. But for other locations, we can relax less. That ratio should be less than or equal to 60. So these things can happen, especially in the smaller shear wall thickness. Normally, when we design for the buildings in high seismic zone, due to large shear demand, we have to provide thickness, large thickness. Let's say 800 millimeter, 700 millimeter thickness of the wall. But in the low seismic zone, we may not need that thickness in the shear wall for shear capacity or moment capacity. In those walls, we may use 200 millimeter or 250 millimeter thickness. In that case, those local buckling can happen. For example, height of the story is, let's say, 3 meter story height. And if we have 300 millimeter thickness wall, so this condition will be satisfied. If you have 300 or 400 millimeter wall, this one will be satisfied. But if you use 200 millimeter thickness wall, this condition may not be satisfied, and it can create the local buckling if you have large stresses. But if you want to check in details, you can check with this curve. This one is based on the maximum tensile strength, and use this formula. But this one is the shortcut for this formula. Here in this picture, the shear wall. In the shear wall, there will be boundary zone element. As you can see, a lot of confinement reinforcement provided at the boundary zone, and also large vertical reinforcement. But here in the middle zone, the vertical reinforcement is reduced, and also there is no confinement. Normally, we concentrate the vertical reinforcement at the boundary zone. So, the advantage is if we provide the large vertical reinforcement, we can use that vertical reinforcement to support the confinement reinforcement. We can tie the confinement in those vertical reinforcement. Not only that, not only for that construction, for the curvature capacity, it can also increase, like the compression reinforcement in the doubly reinforced beam. If you have larger compression reinforcement, you will have good ductility. For example, in doubly reinforced beam, for example, singly reinforced beam, if you have only bottom reinforcement, no top reinforcement for compression, you will get let's say 500 kilonewton meter moment capacity, yielding capacity. But if you provide top bars for the compression, the moment capacity is not significantly increased. The beam become doubly reinforced. Moment capacity is almost same, little bit increase, but the increase is the ductility. The moment curvature curve will become more ductile. Same thing in the shear wall. For example, due to the earthquake, there is a moment. This one is compression and this side is tension. If you provide more vertical reinforcement at the corner, these vertical reinforcement will act as a compression steel in the doubly reinforced beam, and it will enhance the curvature capacity. I want to also show the ETAB's model. Okay, sorry. It improves the curvature capacity, and also this reinforcement, local reinforcement ratio increase will promote the better distribution of flexural cracks. The flexural cracks under seismic loading will be distributed properly, not only one large crack during the earthquake. So these are the boundary elements in the shear walls. So for the boundary zone elements, how we have to decide whether we need that confinement or not. In ACI 318, it suggests two methods. One method is displacement method, and another method is stress-based method. In displacement method, you have to check the displacement at the top of the wall, but that method will work for planar walls. For the complicated configuration of the wall, I recommend to use stress-based approach. So we have to check the compressive stresses in the shear wall from the final element model. You analyze the building and then you have to see the compressive stresses and then check from your shell stresses whether that stress is more than 0.2 F prime C or not. If that stress is more than 0.2 F prime C, you have to provide the special boundary zone in those locations. But you have to also provide until the stress lower than 0.15 F prime C. I will show you from sample model. In this building, I will show the shear wall at grid line B. And I will show the stresses. You have to change to shell stresses and check S22. And by objects, for example, in this shear wall, we use the concrete compressive strength of let's say 41.4 megapascal. So if we go to 0.15 F prime C, so it will be 1.4 into 0.15. So it will be about 6.2 megapascal is the limit. So I will make a limit of
กูไม่เกี่ยวแอคทีฟหน้าจอแต่นี่สักอย่างใส่ใช้ใส่ไหม
I will make a limit of 6.2 megapascal and then I will see the stress diagram. I will define one response spectrum case.
ไม่ค่อยได้คุยเรื่องนี้ว่ะ Ani baru.
I will continue the presentation and one analysis finish. I will explain. So those confinement at the boundary zone, we have to check based on the stresses. But those stresses, for example, we see the stress, and if stress is more than 0.15 FC prime from base foundation to level 4, so we have to provide the special boundary zone until level 4, and then we can reduce the boundary zone reinforcement. So you know the first you decide the until which level we need to provide the boundary zone reinforcement, and we have to, and also we have to check to what extent, to what length we have to provide the boundary zone reinforcement in the shear wall. That one, the code mentioned that length LBE should be greater than or equal to maximum of C minus 0.1 LW. C is the neutral axis depth, and this is 10% of the length of the wall. So from that equation, you can decide the length of the boundary zone. Now you know the until what height and until what length you have to provide the confinement reinforcement. But you have to calculate what is the steel area of the confinement reinforcement. The code mentioned that reinforcement will be 0.09 square root of 0.09 F prime C divided by FYT. So that is the steel area of the confinement divided by spacing of that confinement into this PC. This this dimension, confined concrete thickness. So here ASH is, for example, in this direction for this wall we have to check for the confinement area in this direction. 1 leg, 2 leg, 3 leg. Okay, so you have 3 legs of confinement. Let's say you are using 12 millimeter dia bar with 3 legs, so 3 into area of 12 millimeter dia bar divided by S is the vertical spacing. What is the spacing of those confinement? For example, if you use the vertical spacing of 100 millimeter, this one will be 100. BC is this thickness of the confined concrete. So you have to use that equation to calculate the required confinement area. And also there are dimension limits of those confinement. These who says that spacing should not be more than this criteria, and also this horizontal spacing of these confinement should not be more than this criteria. So you have to satisfy those requirements. So if our stresses are small, compressive stresses are small in the upper floors, we can relax the confinement reinforcement. In that case, we can use this detailing, we call it ordinary boundary element, and just provide the minimum confinement we normally provide for the tall buildings. In high seismic zone, we use 16 millimeter dia with the vertical spacing of 150 to 200 as the ordinary boundary confinement. Here there is no specific steel area calculation equation. So this is the typical detail of the confinement reinforcement in the shear wall. This is in elevation view. So we check 0.15 F prime C from the stress contour of the final element model. If needed, we have to provide until this zone. And we calculate the boundary zone length from the equation and calculate the confinement, required confinement, and provide. But in the upper level, we can reduce the confinement. This is ordinary boundary zone element. But we still provide until, although the ties are not required, we normally provide until to the top. So when you design the vertical reinforcement for the bending moment capacity, first you have to determine the boundary zone element requirement. Okay, do not calculate the how much vertical rebar we need directly. We have to calculate the boundary zone element is required or not. If it is required, we have to determine the length of the boundary zone. It is 1 meter or 1.5 meter. We have to determine. Then we have to calculate the required boundaries confinement area from ASH divided by S into P. That equation, we calculate the number of legs and spacing of the confinement. After we get those spacing and confinement layout, we will provide the vertical reinforcement according to that layout in the ETABs or other software. Then we calculate the curve for that vertical rebar layout. Then we have to check our load demand P and M values are within the capacity curve or not. If it is not satisfied, we have to increase the vertical reinforcement diameter or the number of vertical reinforcement. Another one is the shear design of the shear walls. So for the shear design of the shear walls, in the code, it mentioned that if we, for concrete components, if we do not check the probable shear demand based on the moment capacity of the members, we have to use phi equal to 0.6. If we check the probable shear demand, we can use phi equal to 0.75. But for the shear walls, it is difficult to check the probable moment capacity, shear demand based on the moment capacity. So we have to use either 0.6, or we can amplify the shear demand by the moment capacity of the wall divided by moment demand, and we can use 0.75. So for example, if your shear demand from the load combination is 10,000 kilonewton, and this is like a moment DC ratio, you design the shear wall of this demand to capacity ratio of 0.8. So it will be 1 over 0.8, and you will get the factor and multiply that factor with the shear demand. So you will have the amplified shear demand. Let's say that factor is 1.2. You have to multiply with 1.2 with the analysis shear demand. So it will be from 10,000 to 12,000 kilonewton shear demand. Then you can use phi equal to 0.75. So either you use lower phi value or larger phi value with increasing the shear demand. But people suggest to use this second approach, because if we have a large overstrength, this one will be more conservative instead of compared to using amplified shear with 0.6. This is the shear capacity calculation formula in the code. This one, ACV, is the length of the wall multiplied with the thickness, and alpha C normally 0.17. Okay, because for the tall buildings, walls are slender. Lambda is 1 because this is not lightweight concrete, and this is F prime C, and rho T is the transverse reinforcement ratio. Normally we provide 2 legs of horizontal reinforcement. So, and this one will be the Fy yield strength of the transversity. When we design the concrete, when we design the shear capacity, we have to use this equation, which has concrete shear capacity plus shear capacity of reinforcement. Not only that equation, we have to check the upper limits of the shear capacity of the wall. For example, for the planar wall, we have to check only that planar wall only. But if you have C-shaped wall, you have to check leg by leg. You have to check the flange, upper flange, and the web and the lower flange of the C-shaped wall. You have to check 3 times. So for each leg, you have to check with this equation, and also you have to check the maximum shear capacity limit 0.83 for each leg of the individual leg. If this one is not passed, for example, this equation gives you 15,000 kilonewton. Your shear demand is 18,000 kilonewton. In that case, you have to increase the thickness of the wall. You cannot increase the reinforcement from this equation. You provide a lot of horizontal reinforcement and you are getting 20,000 kilonewton shear capacity from this equation, but from this equation you are getting only 15,000 kilonewton. So the final shear capacity of the wall is 15,000 only. The reinforcement that you provide will not be effective. Not only that, you have to check the combined shear capacity limit. That one is in this building, in the y direction, we have 1 leg, 2 leg, 3 leg, 4 legs. So for y direction earthquake, those 4 legs are resisting together. So you have to get all shear demands in those y direction legs and check with that 0.66 f prime square root of f prime c limit. So this ACV will be summation of concrete area of those 4 legs, and check that one should also pass. If not pass, you need to increase the thickness of the wall. So in summary, in shear wall design, we have to check boundary element and confinement. Second one is the PMM, like a column design. The third one is the shear design of the shear wall. So these 3 checks are important for the shear wall design. For PMM design, you do not need to check leg by leg. For this C-shaped wall, just check as one section for the PMM design. Only shear check, you have to check leg by leg. And also confinement check, when you calculate the neutral axis depth, you have to check leg by leg. But in ETABs, for shear design, confinement check, it can check automatically. I will show you how to check in ETABs later. I will continue for the coupling beams. What we need to link the shear walls, we use the coupling beams. There are 2 types. One is conventional reinforced coupling beam, which is same as the moment frame beam with the longitudinal reinforcement and stirrups. Another one is diagonal reinforced coupling beam. For H, L over H, L is the clear span and H is the depth of the beam is greater than or equal to 4, we use conventional reinforced beam. But if the beam is short or shear stress is high, we use the diagonal reinforced beam like this one. So you can see here diagonal reinforced beam, large amount of diagonal bars coming to the wall. That's why if you have the wall coupled with diagonal bars, you need to have larger thickness to avoid that, because at the corner there will be boundary element of the wall and a lot of reinforcement coming in, so there will be congestion of the reinforcement. Other beams between these 2 ratios, you can design as the conventional or diagonal reinforced beam. This chart shows the selection of diagonal or conventional reinforced beam. For example, if L by D is more than 4, you just design as conventional. If less than 2 and stress is, this is shear stress axis, high, you have to design this region as a, stress is high, design this region as a diagonal. But in this zone, you can design either diagonal or conventional. For conventional reinforced beam, we design the bending moment as a normal beam, special moment frame beam, and we have to provide the longitudinal reinforcement top and bottom. And shear design, we have to design the shear to satisfy the probable moment strength. When we calculate the probable moment strength, we have to use 1.25 Fy, not only Fy. And also you have to use the moment phi equal to 1 for the moment capacity. Based on that, we calculate back the shear and design for that shear. And then we have to provide the confinement at the end.
ETAB หาแม่งไม่มีจะอยากเอาการมาเชียร์มาดีไซน์ห้องใจก็ไม่มีไม่ดีใจเย็นมากเลยนะพี่ดูดิโอ้สองจอเลย
So this is the typical detail of the conventional reinforced beam. At the end, we have to provide the good confinement at the end, here and here. Another type of the coupling beam is diagonal reinforced coupling beam. In diagonal reinforced coupling beam, you have to calculate for the shear capacity only. You do not need to calculate the bending moment capacity. So shear capacity also is based on the diagonal reinforcement only, no concrete strength. So this AVD is the total area of this diagonal reinforcement. For example, you bundle 6 bars in this diagonal reinforcement, use 6 bars area and Fy, and sine alpha is the angle between this diagonal bar and the horizontal direction. And also you need to check the maximum shear capacity limit, like the shear walls 0.83 square root of F prime C. If this stress check is not passed, you have to increase the size of the beam. This is the typical detail of the diagonal reinforced beam, and there are 2 options to confine the diagonals. One is you have the diagonal reinforcement and provide the confinement in the diagonal. That is one way. And another way is you do not provide the confinement in the diagonal, you provide the confinement on entire section of the wall. This one is more easier in construction, because if you provide many confinement along the diagonal, it is difficult to install. But you may need larger confinement reinforcement in this option. An important thing is, when you calculate the alpha, the angle of the diagonal, you have to consider, normally we just calculate this height divided by this length and tangent value of this height to this length. So in that case, when you calculate this height, do not use the height at the top of the, from top to bottom of the beam. This one, if you calculate like this, you will overestimate the alpha value. You have to calculate the height based on this centroid of the diagonal to another centroid of the diagonal. Okay? Do not use from this top to top and bottom. So you have to subtract the cover and subtract the diagonal reinforcement cage, and then you will get the height. So this is for doubling beam design. I will show you how to design the shear wall in ETABs. Let me continue the confinement check, stress check. is surprised why there is no stress. That is a combination. Stress.
เครียดกว่าทำไมว่าอันนี้ขนาดเซียนทำนะไม่เคยทำเลยทำอะไรเชียวสเต็กอะไรอ่ะเชียวจะไม่เชียวจริงบอกอันนี้คือเขาทำแล้วอันนี้เขาจะโมเดลอะไรสเต็กได้เชียวบอกไม่โชว์ได้ไงอ่ะไม่แบบคนตีนี่ตั้งมายังเน่าอย่างไรสั่งแม่นี่ตั้งมาติดเงินถึง20สเต็กคุณบัวเหรียญเขาสมควรสันดาน
I've seen some stresses. So I will limit the stresses to minus 6.2 megapascal, which is 15% of F prime C, and 6.2 megapascal. This should be much.
นี่คือเขากำหนดดีเจียนเอาเท่าไหร่คือเห็นแล้วว่าข้างล่างตรงนี้มัน
Here, from in this shear wall, we can see that I limit 6.2. So you need to provide the special boundary zone from this base to maybe around until level 12. Okay, because the stress is exceeding 6.2 megapascal, and you have to provide until this point, and then until level 12. Then you have to check the boundary zone length from the code equation and provide the confinement. Okay, so you have to decide based on the stress. And I will also show you how to design the shear walls. Let me show you on this planar wall. I make only one load combination here in the meantime, but you have to make all the load combinations that I showed you in the previous presentation. Now I make the load combination which is made AA with the earthquake load, and I will go to design and shear wall design, and first I have to select the design, shear wall design, and first I have to select the load combination. Here I will select only one, but for you, you have to select all the load combinations that you define. And then in shear wall design, there are 3 options. One is simplified CNT design. Second one is uniform reinforcing, and third one is general reinforcing. The first one, simplified CNT, is for, it can be used only for planar walls. You cannot use for the C-shaped wall and other types of wall. So we do not use CNT in our practice because it can be used only for simple walls. You can use either uniform reinforcing or general reinforcing sections. Uniform reinforcing section means the entire section of the wall we design with the uniform reinforcement, not no boundary zone reinforcement, without large reinforcement in the boundary zone. If you use the general reinforcing, you can provide the large reinforcement or whatever reinforcement layout you can provide in the general reinforcing section. First, let me show you with the uniform reinforcing. So in that one, you have to select the concrete strength that you use, and then bar size you want to use. I suggest you to start with 25mm dia bars, and spacing you can decide 250 or, but I prefer to start with minimum reinforce, maybe around 250. And clear cover 25, and end bars also same bars, 25mm. Then you have to select reinforcement to be checked or designed. You have to check reinforcement to be designed because you do not know how much reinforcement is needed. If you already know the reinforcement amount, you just use reinforcement to be checked. So if you choose second option, the program will report you how much reinforcement is required in this shear wall. Then okay, and then let me do the design. Just select this wall, and then I will design it. Design, shear wall design, and start design and check. So in this one, I use 25mm dia in both face with 250mm spacing and check the PMM design.
เราทำเป็นเล็กๆอีกทีไหมว่าเราจะเอาเหล็กที่มันออกแบบให้ไม่หรอก
ข้างล่างมันเยอะอกยันนะครับ
ใช่
มันเริ่มจากข้างบนมาที่อะไร
So from the design, you can see the reinforcement area, or let me go to
เนี่ยตอนนี้สำคัญผมจะดูแล้วที่จะเอา
This is the reinforcement area in millimeter square. If you want to see in rebar percentage, you can also see shear wall design, display design info, and you can see the clear reinforcement ratios. And then apply. So from this one, you can see the required rebar ratio. This is the vertical reinforcement ratio. Okay. Here it mentioned that 0.0 3.36. It is about 3.6% reinforcement at the base, but in the upper level it can reduce. This is based on uniform reinforcing section. Another one is you can also define the general reinforcing section. I will select only one level and go to design, shear wall design, and then assign pier section for. So you can use general reinforcing section here. Okay. In that case, pier section has to define it.
ใช่ใช่มันจะออกมาเป็น
Let's define that
ใน
pier
ที่สุดเราจะรู้ว่า
section
ต้องมาดีไซน์อาหารดีกว่า
น่าจะเป็น
So I have to define the pier sections
ต่อทางเมตรนะลมแล้วตารางเมตร
first for the pier
มัน
labels.
ก็ต้องมาดูอีกรอบหนึงอ่ะพี่
Select the shear wall and then assign
ตัดใส่ไป
shell and pier label. You can define the pier sections, SW1 line. Then based on that, I will define the pier section. Sorry, the shear wall design section. And select it, design, shear wall design, and assign uniform reinforcements.
นี่คือต้องมาที่แบบอันนี้ไม่ขึ้นมาเรื่องนึงเราติดตัวได้
I
แล้ว
have to define it first. Design, shear wall design,
ใช่ครับ
and after define general pier section. Add new pier section, and then I have to select the start from existing wall pier. I already defined the pier label SW1 and assign pier, so I can use the same pier label and then go to section design. The program will automatically add the vertical reinforcement, and you can draw the reinforcement whatever you like. For example, in this boundary zone, if you want to add more, you can add more. And this one also you can add more. And then
เห็นด้วยก็
you
ได้
have to click
แล้ว
OK.
เข้าไปกด
แต่ว่า
เช็ค
อีกแล้วใช่ไหม
เข้าไปกดเช็คก็ได้
You have to give okay,
เข้ามาที่ที่
this
เพราะว่ามันออก
PR
มา
section name
มันจะดีไซน์ให้แบบ0.9
ถ้าเกิดดูที่ว่าไม่พอมึงใส่ไปเช็ครอบ
SW1 design.
แล้วก็เปลี่ยนไซส์แล้วก็เช็ค
Then
ไม่ได้กดดีไซน์แล้วกดเช็ค
then you can assign. Now you use this PR and you use this PR and then assign it to the shear wall sections. Go to design and then shear wall design, assign PR sections and general reinforcing. General reinforcing, so you can see the section that I assign in the define in the section design. Then you have to make reinforcement to be designed and click OK. So that PR is assigned. Then you can decide same as before, but in this time you will get the reinforcement ratio, but that ratio you have to distribute according to the rebar layout that you define in the section design. That portion is complicated. In your term project, you use the uniform PR section, which is just provide the uniform reinforcement, and let the program design for the reinforcement, vertical reinforcement. But for the shear design, I want you to design manually, at least 2 locations, whatever you like. Okay. So for the shear design, I already showed you in the presentation the formulas. So for shear design, you have to get the pier forces of each leg. Let me show you here. Let me select object type. For example, C-shaped wall. You have to assign the peer label with different name. Here, this leg you select it and then assign shell and then peer label. You have to give the name, let's say SW2-1 and apply those, and then 2-2, 2-3. Okay, you have to apply that assign peer names. Then you can extract the peer forces. If you do not assign the peer names, you cannot extract the force in each leg. The program can give you only the shell forces. For example, if you have 3 shells in this leg, you will get the shell forces of each shell, which we cannot use in our design. So we have to use peer label for this leg and get the resultant force for this peer, okay, for the design purpose. After you define the peer labels and assign, you can get the display, show table, analysis, results, and wall results, and you can select the peer forces here. Okay, if you want to filter the load cases, you can filter. Okay, for example, if you want to get the load combination 3 or all load combination, then select it and then show it. So you will get the peer forces of each peer of each level. For shear design, you have to use V2. Okay, that is the shear force in plane direction of the shear wall. So you just check at least 2 locations manually using the formulas. That is easy. So any question on the shear wall design for your TAM project? If you do not have question on the shear wall design, how about the base shear scaling? Do you know how to do? Base shear scaling for now. Okay, you are going to define the response spectrum cases. Okay. Let me show you this. Functions, response spectrum. And then you have to define, I think that one I explained before. Am I right? Okay, you have to define the ASCE 705 response spectrum and define the response spectrum cases. And let me show you. Okay, this one I will not show you, but I will show you the response spectrum cases. The response spectrum cases for X and Y direction, 2 cases. Okay, this is for Y direction case, and then you define with your ASCE function and put 9810 scale factor for the first run. Okay, 9810 scale factor for the first run and analyze it. Then you will get the base shear for that response spectrum case with the 9810 scale factor. 9810. run with 9810, and then we will show display, show table, and then story forces. And I will show only the response spectrum Y. In your case, you have to run for both X and Y. Now you got the story forces, and go to the bottom, story 1. Here you will have Vx and Vy formed from the response spectrum Y with 9810 load case. So you make it SRSS summation of Vx and Vy. Here 1137, 91447, you make it SRSS. So that base shear value will be the elastic base shear value of response spectrum Y case. If you have equivalent, you also define the equivalent static case based on the parameters, seismic parameters, and you will get the base shear from that equivalent static case as well. For example, in equivalent static case, you are getting 45,000 kilonewton base shear. In response spectrum, you are getting 90,000 kilonewton base shear. So you have to scale down the response spectrum case to the equivalent static case. So equivalent static case base shear divided by the response spectrum case, so it will be approximately 0.5. The 0.5 into 9810, so it you have to define another load case, response spectrum case, for the scaling RSY, scaled, and this time you have to put the scale factor, which is around 4,000 in this box, and rerun the analysis, okay, and use that response spectrum cases in the scale cases in your design load combinations. Do not use the response spectrum case which is not scaled, okay. So just scale EQA's equivalent static divided by response spectrum X 9810 case, and get the factor. It is 0.5, so 0.5 multiply with 9810, you will get that new scale factor, and then use that scale factor in your analysis. In this project, you use the you do not have any basement, so you can scale at story 1 or base. But in the real projects, if you have the basements, do not scale the response spectrum base shear below the basement. Always scale above the basement, okay? You will underestimate the base shear, because inside the basement, the story shear is maybe reduced, and if you scale the lower base shear, you will underestimate the design forces. So always scale above the ground level, okay? So that is for response spectrum scaling. Any question? If you have any problem, you can come and email me and discuss with me. Okay, for the first you have to get the correct mode shape, natural periods in the model, then go to the response spectrum scaling and design. The main important one is to get the correct mode shape and the natural period, and the drift displacements are within the limits. The design part is easy because you are going to use the design module from the program directly, only shear check in the shear wall, just manual calculation. So design is fast. Structural system development and making the model will be difficult for you. you.